Hello, friends. Part 3 of the podcast on section 11.2. We're just looking at the graph of the data from problem 11.28, page 709 in your book. And of course, the reason we're going through all this in part A is to talk about normality. And what I would expect to see if this was a normal distribution is something that was a little more symmetric. This looks a little skewed right, doesn't it? So things to keep in mind are that our sample size is 46, so we can stand a little bit askew. And there's no outliers, which is helpful, but there is a gap here. So it's still important to think about how skewed data affects my standard deviation, because that's an important part of the calculation. This all goes back to SOX that we studied right in the fall in September and October. We're looking to describe a one variable set of data. So we talk about the shape, spread, size of the, if there's outliers, and the centers. Part B of this question wants you to decide if this distribution is normally distributed. Why or why not? So why don't you pause this and think about it for a minute. All right. Now, clearly, from looking at this graph, we're going to say it's not normally distributed. However, because the sample size is 46, it's large enough that the central limit theorem says the sampling distribution of x bar is approximately normal. So we're going to proceed to part 3, and it says, does this data give good evidence that the mean change in population is greater than 0? In other words, would I expect, is there evidence in this data to suggest that scores actually go up the second time students take the test? So I just typed this out real quick. This isn't from the book, but these are 3 reasonable sentences which include all the necessary information. The population interest is all the students who take the SAT test twice. I want to find out the average student, if the average student score improves on the second try. To determine this, I'm going to do a z-test where the null hypothesis is mu, which is the average score, stays the same, and see if I have evidence that the mu is actually greater. So the next thing I have to do is talk about the conditions. And here are 3 reasonable sentences to make. Again, I just made these up off the top of my head. It's stated in the problem that the students were randomly chosen and the sample size is 46. And because it's larger than 30, the central limit theorem tells us that the sampling distribution of the mean is approximately normal. And because the population is much larger than 460, I can also assume that it's independent. So now I'm going to do the calculations. I show the formula for the z-statistic. And what I'll actually do right now is perform the z-test on the calculator, because that will give me all of the relevant information that I need. So here's the calculator with the graph still on it. I'm going to go to Stat, 1 left arrow, and I'm going to do a z-test. And this is actually the first time we're doing one from data. So I hit enter, and it asks me what the null hypothesis is, and it's 0. The standard deviation given in the problem is 50. My data is in list 1, frequency 1 again, because I'm just going to count each number in the list twice. And my alternative hypothesis is that the scores should be higher than 0. So I'm going to calculate first, and this should give me all the data I need to write in the calculation section. So when I hit enter, notice it gives me the x bar standard deviation for the sample. That's not what I'm going to use because I'm doing z procedures. And it also gives me the z-statistic and the p-value. So I get a z-statistic of 1.778 and a p-value of 0.0377. It means I would expect an x bar, a sample average, this high or higher only 3% of the time, 3.7% of the time, if the null hypothesis is true. So if scores are the same, if they don't really go up, I'd get a result this high only 3.7% of the time. Now, that means I would reject the null hypothesis if alpha equals 0.05. But if alpha equaled 0.01, I would not be able to reject the null hypothesis. So for homework, see if you can write a good conclusion to this problem.